So, before going into the second part of Chapter 9 worksheet, I just wanted to talk about the VSEPR, which is called the VSEPR theory. So, it's keep in mind that what we did in the first part of the chapter is just learning how to draw Lewis structure, which only give us the correct distribution of the electrons, but doesn't tell us anything about the shape of the molecule. So in order to determine the shape of a molecule, we use what is called a technique that is called the VSEPR theory, which stands for valence shell electron pair repulsion. And what this model assumes is that the electrons distribute themselves about an atom in order to minimize the repulsions between pairs of electrons. Okay, so what do we have here? So if you look at this table, your first step is to get a valid Lewis structure. And then you're going to count, okay, you're going to define the electron set around the central atom. Based on the number of bonding set, based on the number of electron sets, you will determine the electronic geometry. Okay, so based on the number of electron sets, I can determine what is called the electronic geometry. And there's only 3 of them. If I have 2 sets, it's linear. If I have 3 sets, it's trigonal planar. And if I have 4 sets, it's tetrahedral. What is defined as a set? A lone pair, a single bond pair, a double bond, or a triple bond. Okay, so they are defined as one set. You don't count the lines, but you count the group of atoms around your central atom, the group of electrons around your central atom. Then, in order to determine what is called the shape of the molecule, which is the molecular geometry, you will have to identify the kind of sets your electron sets are. As an example, if out of these 2 electron sets, the 2 sets are bonding sets, then you have a linear structure. Out of your 3 electron sets, okay, that gives you the trigonal planar geometry. If all the sets are bonding, then you get a trigonal planar shape. But out of the 3 sets, 2 are bonding and 1 is a lone pair, then you will get a bent shape. If I go to tetrahedral now, a 4 electron set give me a tetrahedral electronic geometry, and out of these 4 sets is 4 of bonding and none are a lone pair, I get a tetrahedral. If 3 are bonding and 1 is a lone pair, I get a trigonal pyramidal shape. And if I have 2 bonding and 2 lone pair, I get the bent shape. Notice that when I add my bonding set to my lone pair, my total is equal to the number of electron sets. Okay, so now let's go to the worksheet. We are asked to find the shapes of the molecule. So let's look at the first molecule here. We're going to determine, in problem 1, we're going to need to find the electronic geometry. So this is solely based on the number of electron group that we have. First molecule has 1, 2, 3 electron group. So if I have 3 electron group, then my electronic geometry is trigonal planar. Out of these 3 electron group, okay, in order to find the molecular geometry, I will see that I have 2 bonding sets and 1 lone pair. This gives me a molecular geometry bent. Second molecule, let's count again. 1, 2, 3, 4 sets. 4 electron set gives me an electronic geometry being tetrahedral. Out of these 4 sets, 2 are bonding sets and 2 are lone pairs. Therefore, I get a molecular geometry bent. Last one, 1, 2, 3, 4 sets. Therefore, again, electronic geometry being tetrahedral. Out of these 4 sets, all of them are bonding, so 4 bonding sets and no lone pair. Therefore, my shape, my molecular geometry is as well tetrahedral. Let's take a look at problem 2 now. We're given that the carbon here is surrounded by 1, 2, 3 group. That's why it's trigonal planar. And each of these groups here are bonding sets. That's why the molecular geometry is trigonal planar as well. Let's take a look at atom number 2, which is this carbon. This carbon is as well surrounded by 3 bonding sets, giving this carbon a trigonal planar electronic geometry. And out of these 4 sets, I see 3 bonding, so it's as well a molecular geometry that is trigonal planar. Carbon number 3, this one here, surrounded by 1, 2, 3 sets as well. These 3 sets being bonding as well, so we have for both electronic and molecular trigonal planar geometry. Finally, atom number 4, which is this oxygen right here. This one is surrounded by 1, 2, 3, 4 sets. Therefore, tetrahedral. Out of these 4 sets, 2 are bonding sets and 2 are lone pairs, which give a bent molecular geometry. Now let's complete the table below, where we're given the Lewis structure of the different molecule. We have the formula in the first column, and we have to determine the geometry of the central atom for each of the molecule. Again, remember that we are only determining the geometry of the central atom here. So my central atom is a carbon, and we're going to first find the number of electron sets. 1, 2, 3 for this first molecule. 1, 2, 3, 4 for this second molecule. 1, 2, 3, 4 for this third molecule. 1, 2, 3, 4 for this fourth molecule, and 1 and 2 for the last one. Now we're going to find the number of bonding sets around the central atom for this first molecule. We have 1, 2, 3 bonding sets. For the second, we have 1, 2. For the third one, 1, 2, and 3. For the fourth one, 1, 2, 3, and 4. And for the last one, 1, 2. What we're going to be looking for now is the number of non-bonding sets around the central atom, which is the number of lone pairs. No lone pair for the first molecule. Look, here on the carbon there's no dots. No lone pair. For the second one, 1, 2 sets that are non-bonding, 2 lone pairs. For the third one, 1. For the last one here, none as well. And for SiO2, none as well. Always check that when I add the number of bonding set to the number of non-bonding, I get the number of electron sets, which means you did a good job. We're going to use the electron sets, the number of electron sets, to determine the electronic geometry. 3 electron sets, trigonal planar. 4 electron sets, tetrahedral. 4 electron sets, tetrahedral. 4 electron sets, tetrahedral. 2 electron sets, linear. Then finally, we're going to take a look at what is the combination between bonding and non-bonding to determine the molecular. We have 3 bonding and no bonding set for this electronic geometry. Therefore, the molecular is as well trigonal planar. For the second molecule, out of these 4 electron sets, 2 are bonding and 2 are non-bonding, therefore bent. For the third one, out of these 4 sets, 3 bonding, 1 non-bonding, give me a molecular geometry that is called trigonal pyramidal. CF4, 4 electron set that are all bonding, therefore it's as well tetrahedral. Stay the same. And for SiO2, out of the 2 electron set, the 2 are bonding, so it's remain linear. What I'm going to go now and talk about is the electronegativity. So I'm going to go at the back here of the handout where you are given the Linus Pauling table here. So the electronegativity is called the power of an atom in a compound to draw the electrons to itself. So it's how much they lag the electron. The higher is this number, and the more the atom love the electrons, so will be more likely to pull the electrons toward its nucleus. Okay. So you can observe that I have a general trend of an increase of electronegativity from the bottom left corner of the periodic table to the top right corner. We're going to use these numbers in order to determine the nature of a bond. And this scale gives you the nature of the bond depending on the difference in the atom electronegativity. So the difference is symbolized by the delta, and we use En to talk about the electronegativity. Therefore, the difference in atom electronegativity is symbolized by delta En. When the delta En is less than 0.5, then the bond is covalent. When the delta En is equal to 0.5 and less than 0.2, less than 2.0, sorry, then it's polar covalent, so includes the 0.5. 0.5 is polar covalent, but less than 2.0, sorry, so exclude the 2.0. And finally, ionic bond when the delta En is greater than 2.0. So, what does this mean? When I have a covalent bond, this means that the electrons are, the electrons are shared evenly between the two atoms. In a polar covalent bond, what I have here is that the electrons are shared unevenly between two atoms. And if you remember the definition of a ionic bond, the electrons are transferred. So they're not shared. Okay? Covalent bond only formed between two nonmetal. An ionic bond only form between a metal and a nonmetal. Okay? What we've seen in chapter 5. These are information from chapter 5. How do we represent a polar bond? Imagine that I have an atom X and an atom Y. If the En of X is greater than the En of Y, in the case where my delta En between X and Y is greater than 0.5 and less than 2.0, then I have what is called a polar covalent. If X is more electronegative than Y, X like the electrons more than Y. Therefore, the electrons that are represented by these lines, this line are toward X. And this will create the formation of, a disruption of the electron cloud between the X and the Y. And now this X has a slight excess of electron represented by the delta negative, and the Y's as a slight default of electrons represented by a delta plus. These delta charges are called partial charges, and we're just trying to show here that we have an uneven distribution of electrons between the two atoms, which generates those partial charges. Okay? We will be able to represent a polar bond by an arrow, that is a vector, okay? And we draw this bond vector from the less electronegative atom to the more electronegative atom, so from the plus to the minus. And this bond vector, okay, will be proportional to the difference in electronegativity, and these vectors have both length and directions in space. Sorry, so if I go back now, not to this one, to the back of this page. Polar bonds and molecule. Which bond is more polar, CO or FS? So let's do this. So we have two bonds here. We have CO and we have FS. We're going to grab the scale to determine the electronegativity of each. Carbon has an electronegativity of 2.5. By the way, the electronegativity have no units. Oxygen is 3.5. F is 4.0. S is 2.5. We will calculate the delta En, which is the difference between the two. So 3.5 minus 2.5 give me 1.0. 4.0 minus 2.5 gives me 1.5. Just when you do your delta En, it's the absolute value, so it's the greater En minus the smaller En. When we look at these two numbers, they're both greater than 0.5 and less than 2.0. So we are in presence of two polar bonds. But because the delta En of Fs is greater than the delta En of CO, this bond here is more polar. Okay, so which bond is more polar? Fs, because the delta En of Fs is greater than the delta En of CO. We're going to use the delta plus and delta minus notation to show the more positive and negative ends of each of the polar covalent bond. Remember that delta minus get to the higher delta En, the higher En, and the delta plus on the other side. And then to show the polarity of the bond, we're going to use an arrow from the least to the more electronegative atom. And this arrow will be smaller than that one because the delta En of Fs is greater than the delta En of CO, and this is proportional. What we will do is we'll combine the VSEPR model, so the shape of the molecule, and the fact that the bonds are polar to determine if a molecule if a molecule is polar or non-polar, so to determine the polarity of a molecule. And then what we will do here is you're told in problem 5 that each of these molecules have a net dipole. We will need to show the direction of the polarity for each individual bond, and then we're going to combine these bonds, okay? We're going to actually sum all the bond vector, and if the sum of all the bond vector is 0, then the molecule is non-polar. And if the vector sum is not a 0, then we have a resultant that is called the dipole moment, the net dipole. And if we have a net dipole, then this molecule is overall polar. So again, the net dipole is the sum, the vector sum of all the bond vector. So what I'm going to do is first write down all the En of every single atom. So here 3.5 for O, 2.1 for each H, so H is 2.1. You find these numbers on the table, the electronegativity table. Chlorine is 3.0, carbon is 2.5, and N is 3.0. Okay, therefore, let's take a look at the individual bond, this one and that one. We have here a delta En equal to 1.4, 3.5 minus 2.1. Therefore, each of the OH bond is polar covalent, where the electrons are pulled toward the more electronegative atom, which is the oxygen. When I add these two vectors together, I get an overall, and I'm going to use purple for the overall net dipole that is pulling to the top. Therefore, I do have a net dipole, and if I have a net dipole, this molecule is said to be polar. Second molecule, we're going to do the same thing. We have here 3 identical NH bond. We're going to take a look at one here. The delta En being 3.0 minus 2.1, 0.9. So I have as well 3 polar covalent bond with 3 bond vector, and is more electronegative, so all the bond vector are pointing toward the end. Therefore, I have a net dipole moment going up, and if I have a net dipole moment, this molecule is polar as well. Last one. So we have different kinds of bond. We have CHs. The CH bonds have a delta En equal to 2.5 minus 2.1, so 0.4. Therefore, these bonds are pure covalent. And if they're pure covalent, there is no bond vector, since the electrons are evenly shared. The second kind of bond we have is the CCl. If we do these ones, the delta En is equal to 0.5, which make this bond slightly polar covalent, where the electrons are pulled toward the Cl. The last bond, the CC, with a delta En of 0. Therefore, pure covalent, nonpolar. Okay, and no bond vector. When I add these 2 green arrows together, I get a net dipole pointing toward the bottom, and this net dipole presence tells us that this molecule is polar as well. So we have here 3 polar molecules. Last problem now, where we have 3 molecules. We have to draw the Lewis structure, identify any polar covalent bond, and state whether the molecule has a net dipole or not, and then show the direction of the net dipole. So, first molecule, BCl3. We're going to draw the Lewis structure. Therefore, in order to do that, we have to follow our step-by-step procedure. For this molecule, we have 3 for the boron, plus each chlorine brings 7, a total of 24 valence electrons. The boron is central. 3 chlorine surrounding the boron. We're going to connect the Cl to the B, and we use 6 electrons. We're left with 18 electrons that we're going to use to give an octet to each outer atom. There is now 18 electrons used and none left. Remember that the boron, okay, is one of the exceptions, and boron and Be may have less than the octet because they are not very electronegative. Be, beryllium, is actually stable with 4, and boron is stable with 6. So here we have a correct Lewis structure. Now that we have this Lewis structure, we're going to take a look at the number of bonding sets. We have 3, the number of electron sets. We have 3 electron sets. These 3 sets are all bonding. Therefore, we have a trigonal planar molecular shape. We're going to draw it with an angle of 120 between each chlorine atom. And now we're going to take a look at the nature of these bonds. The delta En for BCl is equal to 2.0, the difference between 2.0 and 3.0, so 1.0. Therefore, this bond is polar covalent. And the electrons are pulling toward the Cl. What happens here is that when I do the sum of the vector, the three vectors are equal and they are at a 120 angle to each other. So the sum of all the bonds vector is 0. Okay, the sum of all bond vectors is equal to 0. Therefore, there's no net dipole. And if there's no net dipole, the molecule is nonpolar. Second molecule, FCl. F 7 valence, Cl 7 for a total of 14 valence electrons. FCl, I connect them with one line, therefore I used 2 electrons. And I'm left with 12. I'm going to use these 12 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Fulfill the octet rule for both F and Cl. Take a look at the fact that I only have one bond, so the shape of this molecule can only be linear. Okay, since I only have one bond, one electron set, it can only be linear. Once we have this, here is our molecule being linear. F as an En of 4.0, Cl as an En of 3.0. So the delta En is equal to 1.0, again, which give me a polar covalent bond where the electrons are pulled toward the F. There's only one bond, therefore the net dipole has the same direction. I do have a net dipole, therefore this molecule is polar. And why is this important? Since BCl3 is nonpolar and FCl is polar, these two molecules are not miscible. On the other hand, now let's take a look at Cl2. SCl2, 6 electrons for S. Each chlorine brings 7 for a total of 20 valence electrons. S will be central to chlorine, used 4 electrons to connect, have 16 electrons left, give an octet to the chlorine, used 12 electrons to give an octet to the chlorine, have 4 electrons left that I'm going to give to the sulfur. That's the lowest structure of SCl2 because all of my atoms have an octet and all the valence electrons have been used. I have 1, 2, 3, 4 electron sets. Out of this 4 electron sets, I have 2 bonding and 2 non-bonding. So this is a bent molecular shape. This molecular shape is bent from the tetrahedral electronic geometry. We're going to be able to draw this one as being bent okay? Just for information, because it's from tetrahedral, this angle here will be 109.5 degree. Let's not use an arrow, it might be confusing, so just the angle here will be 109 degree, 109.5. Take a look at the bond now. S has an En of 2.5, Cl of 3.0, so an delta-En just on 0.5, which makes this bond polar covalent, pointing toward the Cl. When I add these two vectors together, I get a net dipole going to the bottom of the page. So here is my net dipole. Because I have a net dipole, SCl2 molecule is polar. And why again? Why do you think this is important? Because if I have two polar molecules, then SCl2 and FCl are miscible. Polar dissolve polar, non-polar dissolve non-polar. So I can use the polarity of a molecule to determine if two substances are miscible, which means can be mixed together, or two substances are immiscible, not miscible, which means they cannot be mixed together, which is the case of oil and vinegar, because oil is nonpolar and vinegar is polar, and for that reason you cannot mix oil and vinegar.